Hello everyone and welcome to my final presentation for EE432 Advanced Computer Vision. My name is Mo Wu and I'm a graduate student majoring in electrical engineering. Today I'm really excited to share my literature survey titled Efficient Neural 3D Scene Representation, a survey from NeRF to Gaussian splatting on edge devices. Let me start with a quick overview of what I'll cover today. This presentation is organized into several parts. First, I'll introduce the background and the main goal of this survey. Then I'll explain the core tasks and hardware challenges when deploying these models in real systems. After that, I'll go through three major optimization directions that researchers are currently exploring: optimizing implicit models, optimizing explicit models, and hardware-software co-design. Then I'll present a comparative analysis that highlights the trade-offs between these three approaches. Finally, I will discuss future research directions and conclude the presentation. Before diving into the technical details, let's first look at the pictures. Over the past few years, computer vision and computer graphics have gone through a major paradigm shift. Traditionally, 3D reconstruction relied heavily on classical geometry-based techniques, such as structure from motion or multi-view stereo. These approaches explicitly reconstruct surfaces or point clouds. However, more recently, researchers introduced continuous neural scene representations, most famously neural radiance fields, or NeRF. NeRF models are seen as a continuous function represented by a neural network. This approach produces extremely high-quality photorealistic renderings and quickly became a major breakthrough in neural rendering. Even more recently, another representation called 3D Gaussian splatting, or 3DGS, has emerged. Instead of relying on a neural network, 3DGS uses explicit 3D Gaussian primitives to represent the scene. The key advantage is that it dramatically improves rendering efficiency while still maintaining very high visual fidelity. So overall, the progress in this field has been incredibly impressive. However, this leads to an important practical question. How do we actually bring these high-fidelity 3D scene representations out of the research lab and into real-world systems? In many academic papers and even in our class, we usually evaluate these models on powerful desktop GPUs. But in real-world applications, things look very different. For example, autonomous driving platforms such as NVIDIA Drive Orin, wearable AR or VR headsets, mobile robotic systems, all of these platforms operate under strict hardware constraints. They have limited power budgets, limited thermal envelopes, and much smaller memory capacity compared to desktop GPUs. At this point, a natural question might be, why not simply offload everything to the cloud? In theory, that sounds convenient, but in practice, it causes several serious problems. First, cloud processing introduces unpredictable network latency, which can be dangerous in safety-critical systems like autonomous driving. Second, transmitting large volumes of visual data requires massive wireless bandwidth. And third, sending raw sensor data to the cloud also raises significant privacy concerns. Because of these issues, many applications require on-device processing. In other words, we need to deploy these neural rendering models directly on local edge hardware. And that is exactly the central focus of this survey. The goal of this work is to systematically review optimization techniques that allow modern neural scene representations to run under strict edge hardware constraints. Once we attempt to deploy these models on edge devices, we immediately encounter two major hardware bottlenecks. Interestingly, the bottleneck actually depends on which representation we use. Let's start with implicit representations, such as the original vanilla NeRF. NeRF represents the scene using a multi-layer perceptron, or MLP, to render a single pixel. NeRF performs a process called volumetric ray marching. Basically, the algorithm samples hundreds of points along each camera ray, and for every single point, it queries the neural network to estimate color and density. As you can imagine, this results in an enormous number of MLP evaluations. In other words, the computation cost becomes extremely high. This makes NeRF heavily compute-bound. The required floating point operations quickly exceed the power and thermal limits of mobile system on chips. As a result, the frame rate on mobile devices often drops to less than 1 frame per second. Now let's look at the other representations. Explicit models, such as 3D Gaussian splatting. 3D.js completely avoids the expensive MLP evaluations. Instead, the scene is represented using millions of explicit Gaussian primitives, and rendering is done through a tile-based rasterization pipeline with alpha blending. This greatly improves computational efficiency. However, this introduces a different problem. Each Gaussian stores many attributes in 32-bit floating point precision, including 3D position, covariance matrix, opacity, and spherical harmonics coefficients for color. When you have millions of Gaussians, the total memory footprint becomes extremely large. Fetching this data creates a serious memory bandwidth bottleneck. As a result, 3D.js becomes memory-bound, and it can easily cause out-of-memory crashes on mobile devices. So, to summarize, NeRF suffers from a compute bottleneck. 3D.js suffers from a memory bottleneck. Because of these dual challenges, the research community has proposed many optimization techniques. In this survey, I grouped them into three main directions: optimizing implicit models, optimizing explicit models, hardware-software co-design. Next, let's go through each of these three approaches. The first direction focuses on compressing implicit models like NeRF. The key challenge here is reducing the large number of MLP queries while still maintaining good image quality. One effective solution is called grid-based baking. A representative method is mobile NeRF, proposed by Chen and colleagues at CVPR 2023. The core idea behind mobile NeRF is actually quite clever. Instead of evaluating the neural network at runtime, the method bakes the neural representation into a discrete structure, specifically textured polygon meshes. So essentially, the continuous neural field is converted into something that traditional graphics hardware can render very efficiently. The big advantage of this approach is that it leverages the highly optimized Z-buffer rasterization pipeline already available on standard mobile GPUs. In other words, we replace the expensive volumetric rendering process with standard mesh rasterization and lightweight fragment shaders. This allows mobile NeRF to achieve interactive frame rates on ordinary smartphones, which is quite impressive. However, this approach also comes with an important limitation. The baking process often trades computation cost for memory usage. A densely baked feature grid can consume gigabytes of RAM. For edge devices with limited memory capacity, this can easily create a new memory bottleneck. Now let's look at the second direction, which focuses on compressing explicit models like 3D Gaussian splatting. Since the main issue here is memory usage, the goal is to reduce spatial redundancy and lower the precision bitwidth of stored attributes. One commonly used technique is codebook dictionaries combined with vector quantization. A representative example is Compact 3D GS, proposed by Lee and colleagues at CVPR 2024. In standard 3D GS, the spherical harmonics coefficients used for color representation can occupy up to 80% of the total memory. Compact 3D GS suggests this by applying k-means clustering to build shared codebooks for colors and scaling factors. Instead of storing full FP32 values for each Gaussian, the model stores a small index that references a shared dictionary. This dramatically reduces the model size. In fact, this method can achieve compression ratios greater than 10 times, which significantly lowers the memory footprint. Of course, there is also a trade-off. Reading attributes from a codebook requires a small decoding step during rendering, which introduces a minor delay. But in practice, this trade-off is very reasonable because it prevents out-of-memory failures on edge devices. Another complementary technique is structural pruning. For example, methods like light Gaussian compute global significance metrics and remove Gaussian primitives that contribute very little to the final image. Many Gaussians may have near zero opacity, meaning they barely affect the rendering result. By safely removing these redundant primitives, we can further reduce both memory consumption and sorting overhead on mobile GPUs. So far, we've looked at algorithm-level optimizations, but in many cases, algorithmic improvements alone are not enough to meet real-time performance targets on edge hardware. This brings us to the third and most fundamental direction: hardware-software co-design. General-purpose GPUs are designed to support many different workloads. However, neural volume rendering often involves irregular memory access patterns that GPUs are not optimized for. Because of this mismatch, researchers have begun designing domain-specific hardware accelerators. One example is the Icarus architecture, which separates point sampling and neural evaluation into specialized hardware pipelines. This design allows the system to process these tasks asynchronously, improving the throughput. And even more radical idea is compute in memory, or CIM. Traditional computer architectures follow the von Neumann model, where data must constantly move between memory and processing units. This data movement consumes a large amount of energy and time, especially when dealing with large neural network weight matrices. CIM architectures attempt to solve this problem by embedding computation directly inside memory arrays. Using technologies such as RRAM, the system can perform operations directly where the data is stored. The key advantage is that it almost completely eliminates the data movement overhead, which leads to orders of magnitude energy savings. However, there are also practical challenges. Designing and fabricating specialized ASIC chips is extremely expensive and time-consuming. In addition, such hardware can be less flexible when algorithms evolve quickly. Therefore, in the short term, most practical deployments will still rely on FPGAs or embedded NPUs. To better understand the trade-offs between these approaches, I compiled a quantitative comparison matrix. This comparison evaluates both visual quality and hardware efficiency metrics such as frame rate and memory usage. One clear observation is the paradigm shift between different representations. For example, vanilla NeRF has a relatively small memory footprint, but it runs extremely slowly on edge hardware, often below 1 frame per second because it's compute bound. On the other hand, vanilla 3D provides excellent visual quality and very fast rendering. However, it typically requires between 4 and 10 gigabytes of RAM, which exceeds the memory capacity of most mobile devices. Interestingly, the current sweet spot for edge deployment appears to lie in compressed, explicit models such as light Gaussian. By combining pruning and quantization, light Gaussian reduces the model size to about 30 megabytes, while keeping the RAM usage below 1 gigabyte. More importantly, it can achieve over 60 frames per second on mobile hardware. This is particularly important for applications like mobile AR and VR, where high frame rates are essential to prevent user motion sickness. Similarly, in robotics applications, frameworks such as GSLAM use explicit representations to provide much faster checking compared with traditional NeRF-based SLAM systems. This brings us to the final part of the presentation, future directions. According to the project guidelines, one question we should consider is, if we had one more month to extend this project, how would we improve it? I would like to say if I had additional time, I would focus on-device training and adaptation. Right now, most edge frameworks are designed mainly for inference, not training. However, in real-world scenarios, such as a mobile robot exploring an unknown environment, the system must continuously update its map. This can cause unbounded memory growth. To address this, I would study online continual learning frameworks such as PocketGS, which demonstrate that on-device 3D-GS training is feasible even under strict compute constraints. More broadly, there are still two major open challenges in this research area. The first challenge is dynamic sinks. Most current compression techniques assume static environments, but real-world sinks often involve moving objects, deformable structures, and temporal changes. Handling these scenarios requires 4D Gaussian splatting, where time becomes an additional dimension. Designing temporal smoothness-aware compression strategies for 4D sinks will be an important research direction. And the second challenge is unified hardware accelerators. Algorithmic compression can only go so far, so to truly overcome current performance bottlenecks, we need hardware architectures that natively support operations required by 3D-GS, such as rasterization and depth sorting. So one promising example is the NEO architecture, which introduces a reuse and update sorting mechanism. This design could potentially address the memory bandwidth limitations faced by current 3D-GS pipelines. To conclude this survey, we can observe a clear trend in the field. Neural rendering on edge devices is gradually shifting from purely algorithm-driven improvements toward hardware-aware design. Implicit models like NeRF establish the original foundation of neural scene representation. However, explicit representations, especially 3D Gaussian splatting, combined with vector quantization and parameter pruning, currently show the greatest potential for real-world edge deployment. These approaches strike a strong balance between high visual quality and strict memory and power constraints. Thank you, Professor Wu, and thank you to everyone watching this presentation today. I really appreciate your time and attention. And I hope this talk provided some useful insights into the intersection of computer vision, neural rendering, and edge hardware systems. Have a great day.